Now it's time to have a look to a practical example to see how the choice of the instrumentation is reflected into the compiled target binary. To show the differences between the two compilers, we will use this simple program. The main function reads the first command line argument as int and assigns it to the num variable. Then it calls three different functions. The first one is handle 0 if num is equal to 0, handle positive if num is positive, and finally in the else statement we have handle negative. Don't worry about the content of the three functions because it's not relevant for this example. So now we can compile it like we did before using AFL fast. And the first things to do is to open our AFL container and we mount the project directory under target. So we go inside target, we create the build directory, and we compile it. So again, we use AFL fast and AFL fast++ for C++. Finally, we can make it. Now we have our compiled binary that we can decompile it using our favorite decompiler. For example, in this session, I will use Ghidra. Let's open Ghidra. Okay, and create a new project. We can call it number check. Now inside our project, we import the number check binary that we have inside the build directory. Okay, double click. Yes, nice. In AFL, the coverage map is the AFL area pointer. AFL area pointer is an array that is accessed every time a new area is reached. This can be seen, for example, in the recompile C of the main function. So if we click on the main function, we can see that in line 11 that the array is accessed. The same can be seen, for example, in line 21, 27, and so on. Notice how there is an access to the AFL area pointer at the top of the main function and also inside the if statement and in the else. So basically there is an access to the AFL area pointer array every time there is a new branch in our code. In PCGuard, the index of the AFL pointer array is accessed in a deterministic way at runtime. Specifically, the value of the that something variable, is populated at runtime. This can be seen also in the assembly code on the left, where we can see that the value, the index, is being loaded into the RAX registry. To compare it with LTO mode, we have first to recompile our binary in LTO mode. So we jump back to our container, we create a new folder, for example, build2, go inside, and we call again the cmake command, but this time, instead of using AFL fast, we are using AFL LTO for C and LTO++ for C++. Now we can make, and we have the new number check binary, but this time it's compiled in LTO mode. So we can jump back to Ghidra, not this one. Here, we can import a new file, this time build number 2, and we can call it number check LTO. as you can see in the main, we have again the AFL area pointer, but this time is accessed using a static index. So if we go a bit below, we can see that we have other access to the array, and every time with a different static index. If you want to know more about how it works under the hood, you can check the source code of AFL. Explaining the full implementation is of course out of scope for this course, but we can point out some key functions. We can start, for example, by looking to the AFL clang-fast and the AFL clang-LTO commands inside our AFL container, and what we can see is that they are just links to the AFL CC binary. So if we move inside the source code of AFL, in particular AFL cc.c, into the main function, we can see that one of the first functions that is called is compiler mode by calle. Looking inside, we see that it checks if the caller is AFL clang-fast on the first row, and in that case, the compiler mode is set to LL1. Otherwise, if the call name is AFL clang-LTO, the compiler mode is set to LTO, and so on with all the other supported modes. So if you want, you can check where the compiler mode is used,